If you remember the first chapters of your previous science textbook, you might recognize that, in Canada at least, all the science textbooks pretty much begin the same way, namely, how does science work? Well, let's review anyway, just in case we forgot some stuff from last year, or previous school years of stuff. Now, skills of scientific investigation. The first thing that should jump out at you is the fact that we're talking about investigation, not skills of science in general. When we do an investigation, what are we doing? Well, we are testing an idea to see whether or not it works, or whether or not it's compatible with the information we get. Or alternatively, we're making observations to try to get an idea of how things work. These all add together to say something. All scientific investigations must be about things that are scientifically testable. So, in other words, if you believe that invisible unicorns make pizza deliveries, that's testable for the simple fact that you can observe how pizza deliveries are made. If you think that invisible unicorns created the universe, that's not testable for the simple reason that you can't, well, test for it. You can't determine. So, scientific inquiries all use the following. They use a variable, which is a factor that can end up being different, or is different. An independent variable is a variable that the experimenter is controlling, or alternatively, the ones that you start with, pretty much, in an experiment. Why is it that technically all the variables you begin with are independent variables? Because they don't depend on the process of the experiment to produce results. And the dependent variables are those results that depend on the independent variables. Why is it that we usually only have one independent variable? Because if we have several, it's hard to figure out messing with what does what. Imagine if you're trying to choose 9 options for your first independent variable and 9 options for your second. That's 81 experiments. It gets a little bit expensive compared to doing 9 with everything else fixed and 9 with everything else fixed. 18 versus 81. Well, you can do the math in terms of how much money you save, or how many % money you save, or fraction if you like it that way. Now, a confounder is what happens when you have independent variables not controlled by investigators. These may produce confusing results. For example, if you have men who are complaining of back pain and women who are complaining of stomach aches, and you give them a particular medication, you can't tell if that medication is better for stomach aches or for back pain, for the simple reason that men and women metabolize drugs differently. This is not sexism. It is fact that there have been sleeping pills that were tested on men and then sold for women. And guess what happened? Well, okay, for the most part, nobody died. But the point is that a lot of women complained that after using the pills, they would wake up and still be sleepy the next morning. Well, it was because women's bodies are more sensitive to that particular drug, or metabolize it slower, i.e. get rid of it slower. So in other words, men are insensitive and chew through stuff too fast. Well, okay, that's one interpretation you can draw from it, but it's not the one we're looking for. The one we're looking for is, how do women metabolize these drugs? And thus, how do we design the drug to be an appropriate dosage for the woman? Or alternatively, for the men. Alright, the 2 main types of scientific inquiry are the controlled experiment, where the experimenter has everything else held constant and takes that one variable, or maybe 2 depending on the case, and then they change that variable and see what happens to the results. So they change the independent variable, they observe the dependent variables, and they see how they are associated by doing this. What's the other way? Well, the other way is an observational study, Why? It's a little bit hard to study the nesting habitats, or the nesting habits for that matter, of dinosaurs. Well, I mean, yes, birds are technically a type of dinosaur, but hey, that's another matter. There is also the fact that sometimes a controlled experiment is less than practical. For example, determining how quickly the planets are orbiting around the sun. How are you supposed to do a controlled experiment for this? Or determining how those planets interact with each other gravitationally. How are we supposed to do a controlled experiment for this? We are not. We watch them very closely. Well, not very closely, but relatively in great detail. Better? Why is it not very closely? Well, we are not very close to them, of course. Now, of course, when you do an investigation, you need to start with getting started. That's what initiating means. Now, how do you initiate a project? Well, you need to think about, what do I want to test? What am I looking for? Where am I starting from? And then you need to plan your experiment. So, your hypothesis is a possible answer or untested explanation that relates the independent and dependent variables. For example, when we are looking at the planets earlier, our hypothesis could be that planets that are farther away from the sun orbit slower. And the independent variable would be distance from the sun, and dependent variable would be orbital period. Alright, hypotheses can give predictions. So, the prediction would be longer orbital period means greater distance, or vice versa, rather. So predictions can be made even without making a hypothesis. How does this work? Well, think about it. If you see a pattern, then you might not be making a hypothesis. There might not be a scientific reason for this pattern, other than, oh, to test your pattern recognition ability. But that's not a scientific reason. The point is that sometimes there isn't a scientific reason. There is no hypothesis to be made, even. So you can still make predictions. Say you have 1 triangle, 2 triangles, 3 triangles. How many triangles do we predict comes next? 4, right? So, a prediction is a statement that predicts the outcome of a controlled experiment. An experimental design, well, okay, obviously after we know what we're looking for, we need to figure out how to get there. So we design an experiment. An experimental design is generally interpreted in science as not just like a plan or schematic, but a brief description of the procedure by which a hypothesis is tested. Why is it brief? The fact of the matter is that sometimes in science you have to change things around halfway through, and therefore excessive detail, well, okay, not only is excessive detail boring to the readers, but excessive detail is often unnecessary and impractical. And then, of course, well, after you plan an experiment, you have to do the experiment, and you record the results. Quantitative results are in numbers. Qualitative results, or observations rather, are not numbers. They're like red cars, blue cars. Whereas quantitative might be, oh, reflection at particular spectra, or reflection at particular points along the electromagnetic spectrum, instead of red cars, blue cars. So, these data points would be quantitative. Why? They're both variables are quantities. They are not qualitative. For example, some plants, well, they have pink flowers in acidic soil and blue flowers in basic soil. That would be qualitative, despite the independent variable being quantitative. Of course, yes, there are in-between cases, but that's relatively few. And if we lump them in a qualitative category, qualitative is also called categorical. Why? because it uses categories as opposed to numbers, quantity. So, analysis and evaluation. If we were trying to correlate the temperature to the price of something, or the revenue from something, then we take some data points that we have, we take our old records, and we plot them, and we put a line of best fit. This is a case of analysis. And if we were asked to evaluate a possible result for 21 degrees Celsius, we can look at our line of best fit and give a rough number. And of course, one of the most important parts of science is to communicate your results. Why? Because you can't earn your PhD without communicating, of course. You can't do anything really without communicating, except do work and not get results, like not get paid or not get graded. So you can't do anything useful without communicating. Fortunately, you are not expected, and indeed you are not recommended, to communicate in anything like this fashion. This is too much clutter. I hope it's pretty obvious that this picture is for laughs and not actually completely serious. At least, I sincerely hope for that man's sake that it is not completely serious. In summary, we do scientific investigations because we're curious about why the world works the way it does. Or, alternatively, we're curious about how the world works. So, we have the controlled experiment where we control most of the independent variables, or all except one, and that one we vary, and then we measure the dependent variables' results. Alternatively, we have the observational study, where we observe and draw conclusions from our observations. Sometimes observational studies are done because they are the only practical way, and sometimes they are done for convenience. Scientific investigations require several different categories of skills, so these include initiation and planning. Well, technically they're one category, but some people call them two. Depending on your regional opinion, you should be careful. So initiation and planning, and then you have to actually do your experiment, so performing the experiment and recording, and analysis and evaluation, and finally communication. Remember, if you cannot communicate, you will not get funding, which means that all your research is completely useless, pretty much. Communication is, well, probably the most important step. Well, hopefully we managed to communicate this to you, and hopefully you will be able to communicate your knowledge of this to your teachers, if they ask for it, of course. Why? Because teachers don't like it when you blab to them too much, usually. Well, anyway, that's it for me blabbing at you today, or for this session.